In this video, we are going to discuss importance of RT minus S square. In my last video, Maxima and Minima part 1, we have discussed the use of RT minus S square in deciding maxima and minima and saddle point of a function of two independent variables. But we haven't studied how did this quantity RT minus S square came into being and what is its importance in deciding maxima, minima and saddle point of a given function. This is exactly what we are going to see in this video. Hello friends, you are watching YouTube channel Number Collage. This channel features videos on mathematical concepts. Effort has been made to explore the concepts through basic mathematical ideas. Hope you will like my effort. You can even check playlist of this channel. Perhaps you might find videos that you are looking for. We have seen for a function z equals fxy with stationary point a comma b has maxima if f a plus h b plus k minus f a b is negative for small values of h and k positive or negative in the neighborhood of, that is very close to, point a comma b, and minima if f a plus h b plus k minus f a b is positive for small values of h and k positive or negative in the neighborhood of, that is closest to the stationary point a comma b, which means for maxima this sign must be retained for small values of h and k. Similarly, for minima, this sign must be retained for small values of h and k. Let us denote f a plus h b plus k minus f a b to be delta. So, when delta is negative for small values of h and k, function f has maxima. On the contrary, if delta is positive, then function f has minima. So we have to focus our attention on the sign of delta, negative or positive, and it should retain its sign for small values of h and k in the neighborhood of a and b. Now it's time we recall Taylor's theorem or Taylor's series as it is called, assuming that fx plus h can be expanded in ascending powers of h. It is expressed as fx plus h equals fx plus h f dash x plus h square upon 2 factorial f double dash x plus h cube upon 3 factorial f triple dash x plus so and so forth plus h raised to n upon n factorial nth derivative of x plus so and so forth up to infinity. On the same lines now, by Taylor's theorem, we will expand f a plus h b plus k in terms of partial derivatives of f a b and h and k. Now by Taylor's theorem, we expand f a plus h b plus k as f a b plus, since z is a function of two independent variables x and y, we have to partially differentiate x and y. So here it will be h fx ab at the stationary point plus k fy ab at the stationary point plus 1 upon 2 factorial h square fxx a comma b plus 2hk fxy ab plus k square fyy ab plus so and so forth. We name this 1. Now since h and k are very small, we can neglect higher order terms h square, hk, k square etc. and write delta, which can be obtained by taking this fab to the left hand side. So here it will be f a plus h b plus k minus FAB, which will be this part, H FXAB plus K FYAB. The necessary condition that delta has the same positive or negative sign is when FXAB this equals 0 and FYAB this equals 0, irrespective of H and K taking both positive and negative values. Now with FXAB and FYAB both equal to 0, neglecting higher order terms h cube, k cube, h square, k square, etc., this equation 1 reduces to this much only. So delta is 1 upon 2 factorial h square fxxab plus 2hk fxyab plus k square fyyab, and we name this. Now we will denote this fxxab by r, fyyab by t, and fxyab by s. So delta becomes 1 upon 2 factorial h square r plus 2hks plus k square t, and we will name this 3. So from 3 we observe that nature of sign of delta depends on the nature of sign of this h square r plus 2hks plus k square t. So now sign of delta equals 1 upon 2r. Taking 1 upon r common, statement 3 becomes h square r square plus 2hkrs plus k square rt, which equals 1 upon 2r. By using these two terms, we will create a perfect square expression h square r square plus 2hkrs. Now we will add k square s square to make this trinomial a perfect square, plus then we subtract k square s square and again add this last term k square rt. Here we have rearranged the terms for convenience. This will be 1 upon 2r. For this perfect square expression we write hr plus ks whole square plus we will take k square common into this rt minus this s square. This being a squared quantity will always be positive, and rt minus s square has appeared here for the first time. Now we will write only those terms which will affect sign of delta. So we write 1 upon r instead of 1 upon 2r into hr plus ks whole square will always be positive, being a squared quantity, and this k square will always be positive even for negative values of k. So what remains is this rt minus s square. This we write over here, rt minus s square. So now if rt minus s square is positive, then the only quantity which is going to affect sign of delta is r. Delta is negative. If r is negative, which means function f is maximum at stationary point AB, and delta is positive if r is positive, which means function f is minimum at stationary point AB. Now what if rt minus s square is negative? Then sign of delta will depend on sign of h and k, which means function f has neither maxima nor minima at stationary point AB. As such, it will be a saddle point. From previous discussion, we have delta equals 1 upon 2 factorial h square r plus 2 hks plus k square t, and we have named it 3, and we also have delta equals 1 upon r hr plus ks whole square plus k square into rt minus s square. We name this 4. Now equating 3 and 4, we have 1 upon 2 factorial h square r plus 2 hks plus k square t equals 1 upon r hr plus ks whole square plus k square rt minus s square. Now if rt minus s square is 0, delta will be 0, and hence this left hand side will also be 0, which means 1 upon r into rh plus ks whole square will be 0. rh plus ks is 0. rh equals minus ks, or h upon k equals minus s upon r. Now this holds only if h and k have opposite signs, which may not be always possible, therefore becomes a doubtful case. Hence we need further investigation. So by now you must have understood the importance of rt minus s square. Viewers, if you like this video, please click the like button. Share this video with your friends and classmates. Subscribe to this channel. Post your constructive comments to make the videos better. You can even check playlist of this channel. Perhaps you might find videos that you are looking for. See you in the next video. Until then, keep watching Number Collage. Thank you.